Hi guys! For today's video, I'll be going to teach you on how to use the 4 fundamental operations in binary and converting data capacity and speed. Before anything else, let's first talk about the binary system concepts. A computer can only understand the on and off state of switch, which are represented by 1 and 0. Binary system works using the same principle as the decimal system, but in this case, the base is 2 rather than 10. For example, convert the binary number 0101 into decimal notation by using the table above. So we have here 0 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 1 times 2 to the power of 0. Then, 0 times 2 to the power of 3 is equal to 0 times 8 plus 1 times 2 to the power of 2 is equal to 1 times 4 plus 0 times 2 to the power of 1 is equal to 0 times 2 plus 1 times 2 to the power of 0 is equal to 1 times 1. After that, 0 times 8 is equal to 0 plus 1 times 4 is equal to 4 plus 0 times 2 is equal to 0 plus 1 times 1 is equal to 1. Add all the values and the decimal notation of binary number 0101 is 5. Or, you can use other method as shown in the table below. 1 times 2 is equal to 2, 2 times 2 is equal to 4, 4 times 2 is equal to 8, 8 times 2 is equal to 16, and so on. Then, put the binary number below, which is the 0101. Add all the corresponding values of bit 1, and in this case, add 4 and 1 to get the sum of 5. But what if we add negative and positive binary numbers? For example, negative 1001 plus 0101. We all know that the decimal value of the first binary number is negative 9 and the second is 5. If we add both of them, the answer should be negative 4. But if we do the math in binary, the answer is 1110 and the equivalent of it is 14. So, it still add the two binary numbers. That's why our next discussion is about sign bit. In sign bit, if the leftmost bit of a binary number is 1, then the number is negative, and if it is 0, then the number is positive. For example, if the binary is 1100, the decimal of that is negative 4. On the other hand, if the binary is 0100, the decimal of that is positive 4. What if we add negative 2 and positive 2? The answer should be 0. But in binary, the answer is negative 4. Still, the answer is wrong, but at least now, we can produce negative numbers. This time, let's talk about 1's complement. In this concept, if the leftmost bit of a binary number is 1, then the number is negative, and if it is 0, the number is positive. Then the rest of the bits will be inverted. It's just like sign bit, but we flip the zeros and ones. For example, if we add negative 5 and positive 5, the answer is 0. But in binary, the answer is negative 0. Still, it is wrong because there is no negative 0 at all, but at least we can produce 0 as the answer. But what if we add negative 7 and positive 2? The answer should be negative 5. And in binary, the answer is also negative 5. There are instances that the answer is correct, but still, using this concept is not accurate. Now, let's talk about 2's complement. In this concept, if the leftmost bit of a binary number is 1, then the number is negative, but it has the value. Then the rest of the bits will be inverted. For example, if the binary is 1011, the decimal of that is negative 5. Because 1 plus 2 is 3, and negative 8 minus 3 is negative 5. What if we add negative 6 and positive 4? The answer should be negative 2. In 2's complement, negative 6 is 1010 and positive 4 is 0100. And if we add both of them, the answer is 1110 or negative 2 in decimal. So, we can say that this concept is more accurate than the previous ones. There is also a technique in finding the negative of a specific number in 2's complement. You just need to write the binary of that positive number, then invert all the bits and then add 1. For example, the 2's complement of negative 4. We all know that the binary of positive 4 is 0, 1, 0, 0. Next is to invert all the bits from 0 to 1 and 1 to 0. And so it becomes 1, 0, 1, 1. Next is to add 1 to the inverted bits. So, the binary of negative 4 in 2's complement is 1, 1, 0, 0. We are done talking about binary system concepts, and now I will be going to teach you on how to use the 4 fundamental operations in binary. But first, let's talk about binary addition. In adding binary, there are 4 rules that need to be followed. 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 1 is equal to 1, 0 or 0 carry 1, and 1 plus 1 plus 1 is equal to 1, 1 or 1 carry 1. For example, 1010 plus 1001. By applying the rules of adding binaries, the answer would be 10011. If we make those binary numbers to decimals, it would be 10 plus 9 is equal to 19. Another example, if we add 100110 plus 110101, the answer would be 10111011. If we change that to decimals, it would be 38 plus 53 is equal to 91. Now, let's talk about binary subtraction. In subtracting binary, there are 4 rules that need to be followed. 0 minus 0 is equal to 0, 1 minus 0 is equal to 1, 1 minus 1 is equal to 0, and 0 minus 1 is equal to 1, but you borrow 1. For example, 100 minus 1. By applying the rules of subtracting binary, the answer would be 011. If we change that to decimal, it would be 4 minus 1 is equal to 3. Another example, 1000 minus 111. The answer would be 0001. If we change that to decimal, it would be 8 minus 7 is equal to 1. Now, let's talk about binary multiplication. In multiplying binary, there are 4 rules that need to be followed. 0 times 0 is equal to 0, 1 times 0 is equal to 0, 1 times 1 is equal to 1, and 0 times 1 is equal to 0. For example, 101 times 11. If we change that to decimal, it would be 5 times 3, and the answer would be 15. When we multiply the multiplier 1 by 1 to the multiplicand, and applying the rules of multiplying binaries, it would be 101 and 101, but the other is moved by 1 place. Then, add both of the binaries and the answer would be 1111. And if we change that to decimal, it would be 15. What if we multiply negative 4 times 4? First, you need to write them in binary, but apply the 2's complement after the operation. So, it would be 0100 times 0100. By applying the rules of multiplying binaries and adding all the binaries, the answer would be 001 0000. After that, we can now apply the 2's complement. Just flip all the bits and add 1. Then the answer would be 111 0000. And if we change that to decimal, the answer would be negative 16, and it corresponds to the answer of negative 4 times 4, which is negative 16. Now, let's talk about binary division. In dividing binary, there are 4 rules that need to be followed. 0 divided 0 is equal to 0, 1 divided 0 is equal to 0, 1 divided 1 is equal to 1, and 0 divided 1 is equal to 0. For example, 1100 divided by 11. 1 divided by 11 is cannot be, so 0. Then, 11 divided by 11 is 1. 1 times 11 is 11. After that, you need to subtract 11 and 11, so the answer is 0. If the remainder is 0 and the remaining bits are 0, then the answer is 0. If we change that to decimal, we know that 1100 is 12, 11 is 3, and 0100 is 4. And if we divide 12 and 3, the answer should be 4. That would be all for the 4 fundamental operations in binary, and now, let's talk about the conversions on data capacity and speed. Let us first talk about the conversions on data capacity. As you can see here, as we go up, we divided it by 1000, but as to bit and byte, we divided it by 8. And as we go down, we multiply it by 1000, but as to byte and bit, we multiply it by 8. For example, convert 9 terabytes to megabytes. Looking to the guide, you need to multiply 9 by 1000 twice so that it will convert to megabytes. So, 9 times 1000 is equal to 9000, and 9000 times 1000 is equal to 9 million. So, our answer would be 9 terabytes is equal to 9 million megabytes. Another example, convert 7 kilobytes to bits. Looking to the guide, you need to multiply 7 by 1000 and multiply it again by 8. So, 7 times 1000 is equal to 7000, and 7000 times 8 is equal to 56,000. So, our answer would be 7 kilobytes is equal to 56,000 bits. Another example, convert 50,000 kilobytes to gigabytes. Looking to the guide, you need to divide 50,000 by 1000 twice. So, 50,000 divided 1000 is 50, and 50 divided 1000 is 0.05. So, our answer would be 50,000 kilobytes is equal to 0.05 gigabytes. Another example, convert 100,000 bits to kilobytes. Looking to the guide, you need to divide 100,000 bits to 8 and divide it again by 1000. So, 100,000 divided 8 is equal to 12,500, and 12,500 divided 1000 is equal to 12.5. So, our answer would be 100,000 bits is equal to 12.5 kilobytes. Now, let's talk about conversions on data speed. It is the same on data capacity, but this time, there are units that are smaller than bit. Namely, kilobit, megabit, gigabit, and terabit. And on data speed, we add per second after it. Also, in internet transfer rate, it uses bits in measuring the internet speed. Because, as to why we measure internet speed in bits, even though the internet delivers bytes of data, it is because the internet delivers those bytes of data as single bits at a time. Furthermore, they have the same patterns when converting, just like multiplying and dividing 1000, or in the case of bit and byte, we divide or multiply it by 8. That will be all for today's video, and I hope that you learned something new about binary representations, most especially to the 4 fundamental operations in binary. And I hope that you also learn about conversions, specifically in data capacity and speed. Thanks for watching.